Right, I just need to X off that. There we go. Great. Yes, so thanks to the organisers for inviting me to speak to you this afternoon. The bulk of what I'll talk about today is a paper that was really spearheaded by David John Gagne, who's at the National Centre for Atmospheric Research, which I worked on, together with Anish Subramanian, who's now at CU Boulder, and Adam Monaghan at the University of Victoria in Canada. In this paper, we use a kind of a toy model to address this more general problem of how we can go about using machine learning tools for stochastic parametrization. Before I get on to the details of that study, I'm going to give a fairly general high-level overview to the problem. There we go. So what is the problem? So what we're interested in is making predictions of this very intricate and complicated Earth system here on the left. So we're interested in predictions at a huge range of timescales. So what happens over the coming days to weeks, so weather forecasts, all the way through sub-seasonal to seasonal forecasts, and then out to our century-long projections. And the tool that we have to make these forecasts, these predictions, are numerical simulators of the Earth system. So my own particular interest is in atmospheric simulators, so in models for the atmosphere, but the things that I say in this talk could equally be applied to other components of the Earth system. But when it comes to the atmosphere, we take the equations of motion that describe atmospheric behavior, so the Navier-Stokes equations, and we discretize these onto some grid. So that's what this schematic is showing here. And so when we do this discretization, of course, we have to define some length scale on which we will resolve the motion. And anything that's occurring at scale smaller than this length scale, which kind of gives us these pixels here, is unresolved. But we have to represent the effects of these subgrid processes back on the resolved scale because it's important for the evolution of the larger scales. And so what we do is we develop so-called parametrization schemes. And these parameterization schemes, to represent these small scales, are naturally simplifications of the small scales. And so when we build these schemes, we have to make certain decisions, certain approximations along the way. And this does lead to errors in our forecasts. And what I want to say is that these errors are actually really quite large when it comes to the forecasts that we're making across the whole range of timescales that we're interested in. So here on this slide, I'm just giving two examples here of how decisions that we make in parameterizations can lead to large impact on our forecasts. So on the left, we have a situation from weather forecasting. So the event that is being forecast here with ensemble forecasts is Hurricane Sandy in 2012. So perhaps you remember Hurricane Sandy. It was a really unusual hurricane because it tracked up the east coast of the US before making this like unprecedented left-hand turn and making landfall in New Jersey. And the interesting thing was that the ECMWF model, so the European Centre for Medium Range Weather Forecasting model, gave a really accurate forecast of this track out to 5 or so days in advance. But the American models did not predict the track at all. So they predicted the hurricane taking a much more kind of right-hand turn out into the Atlantic. And so what the authors of this paper asked was what led to the difference between the GFS model, the American model, and the ECMWF model. And to address this, they took WRF, a separate model, and they implemented the convection, so the cumulus convection parametrization scheme from ECMWF in WRF and from the GFS in WRF. And what we're seeing here is the results of these experiments. So the red lines are showing the WRF predictions when we're using the ECMWF convective cloud scheme. And the blue lines are where we're using the American scheme from GFS. And then the different panels are showing different different initialization dates. So moving from an earlier start date to a later start date. And what we can see is that the differences that were observed in the kind of forecast scale of ECMWF and GFS were completely down actually to the choices that were made in the convection parameterization. So even though, both of these centres have implemented a convective scheme, which they believe is a good representation of the real world, I mean, the specifics of the choices they've made have led to these massive differences in how well the model performs in making these forecasts of Hurricane Sandy. So the second example that I've got here is from climate models. This is from this pretty well-known paper from Zelinka and co-authors in 2020. And what they were looking at is really a first look at the climate sensitivity of the latest CMIP6 models. So here the blue dots are CMIP5 and the orange is CMIP6. And here we're seeing the equilibrium climate sensitivity. So that's how much the kind of globally average temperature will change as a function of doubling CO2. And what you can see is that the average temperature change has gone up for CMIP6, but also the variability has increased. And in this paper, the authors tried to dig in and understand what it was that was leading to this massive uncertainty in climate sensitivity. And what they found was that it could be attributed to cloud feedback. So, and that both cloud shortwave and longwave feedbacks are extremely uncertain in the CMIP6 models. And so again, this is a process which we've parameterized in our model. So the way that clouds are going to respond to changes in temperature, to changes in aerosols, so kind of like particulates in the atmosphere, these are all things that we have to build into our parameterization scheme. And the specifics of the choices we make are leading to massive impacts in the predictions that we make on these longer timescales as well. So what on earth can we do to overcome this problem? Well, perhaps one solution is a brute force approach. Let's just move to a high enough resolution where we start to resolve clouds and convection. So here I'm showing results from this set of runs called the diamond simulations, which were documented in this paper by Bjorn Stevens and co-authors in 2019. And so here I'm showing simulated satellite images from 10 models that are run at a resolution of just a couple of kilometers, and one real satellite image. And so the point that the authors made in their paper is, can you tell which one is the real satellite image? And the thing is, this is obviously extremely impressive, but this is extremely expensive. This is an extremely expensive approach, and we still need to parameterize, because if we're running our models at a resolution of 2, 3, 4 kilometers, we still have to represent clouds. And we still have to represent, in some of these models, they still also represent convection. And before I move on, I'll tell you this one here is the real satellite image. Okay, so perhaps a solution to our problem could be that we move away from our traditional way of building parameterization schemes, and we move to emulating parameterizations using machine learning approaches. And there are two main benefits from this. So the first is that machine learning parameterizations can actually be cheaper than conventional approaches. So by moving to a machine learned parameterization scheme, we can free up some compute resources and then spend this either on increasing our resolution, so moving to those kind of diamond resolution models, including more complexity. So for example, the details of cloud microphysics, so how cloud moves between water, ice, precipitation. We know that this is something that's very uncertain, and moving to a more detailed scheme representing microphysics is very expensive, so we could put that in. We can run our models for longer, so these diamond simulations are only 40 days, so you could run them for much longer than that. We can also run more ensemble members. So more ensemble members could be very important for climate simulations because it enables us to unpick what is internal variability and what is forced response. And there are lots of examples actually of, I'm sorry, I'm getting a bit of feedback. So I was just hoping that everyone could mute their microphones. It's fantastic, thank you. And there's a few examples of how machine learning has been used for this kind of approach to emulate existing schemes. So a lot of work on the radiation scheme has been done by Chevalier and Krasnopolsky over the years. And then more recently, we've had, there's a nice paper from Matt Chantry and co-authors looking at emulating the gravity wave scheme in the IFS. And for both of these, they were able to mimic the performance of these existing parameterization schemes using machine learning, which then really sped up the schemes. And the other benefit of using a machine learning based parametrization is that we can actually improve on our existing approaches. And so we can do this by directly learning what the subgrid closure should be from, for example, a cloud resolving or permitting model, so such as those diamond simulations that we've just seen. Or equally, we could take one of these more complex parameterizations that we would really like to be able to use, so like this more complex microphysics I mentioned, and we could learn then an improved closure of that scheme to sub into our model. And there's been quite a few authors who've done this recently, like a massive burst of work in this area. So both from using global convection resolving models as the benchmark, super parametrization. This is a bit more of a slightly idealized way of doing a convection resolving or a cloud resolving model. And so there's some nice work from these teams here, many papers. And then recently, there's also a paper looking at emulating this more complex microphysics scheme, which came out from David John, who I was working with, as well as other co-authors at NCAR. But the problem is that whatever we do, even if we machine learn a better parameterization scheme, it's still going to have errors. And we've seen that these errors in our parameterization schemes can have very macroscopic impacts on our forecasts on a huge range of timescales. And so really to understand why we're doomed to have errors in our parameterizations, we have to return to some of the fundamental assumptions that are made when developing these kind of deterministic parameterizations. And so to discuss one of the most kind of pervasive assumptions and problematic assumptions, I'm going to return to this very old and widely cited paper by Arakai and Schubert from 1974, which describes the cumulus cloud parameterization problem. And so I've extracted this paragraph from their paper. So they say, consider a horizontal area at some level between cloud base and the highest cloud top. This horizontal area, which we designate as our unit horizontal area, so in other words, this is our grid box, is shown schematically in this figure. It must be large enough to contain an ensemble of cumulus clouds, but small enough to cover only a fraction of a large-scale disturbance. The existence of such an area is one of the basic assumptions of this paper. So what this paragraph is saying is that Arakaya and Schubert are assuming that there is a scale separation between the process which they wish to parameterize, the convective clouds, and the large-scale state. And so we can see that because the convective clouds must be a lot smaller than the grid box, but simultaneously that the grid box must be a lot smaller than anything that's going on in the large scales. And what this means is that within our grid box, we have many, many convective clouds, and that they're all experiencing the same large scale conditions. And so that means that it's meaningful for us to average over this ensemble of clouds to predict what the kind of average cloud would see, and that this would give us a good estimate of what the effect of this cloud field would be back on the large scales. But we know that in the atmosphere, there is no scale separation. So we can never find this optimal grid box size, this resolution at which we should truncate our equations, where everything we need to parameterize is happening on a lot smaller scale, and the resolved scales in the large scales are well resolved. And we can see this by simply looking at kind of power spectrum of motions in the atmosphere. So we see a continuum of kind of energy across all different horizontal scales. So there is no scale at which we see a big dip in this spectrum at which we should put our grid box. And this is also consistent with our kind of experience of the atmosphere. If you look at a cloud field or another field, we see variability on all different scales. So we certainly couldn't pick one particular resolution at which we could put our grid box where we have many clouds consistently within that box. So this then brings us to why we might want to build stochastic parameterization schemes. So we recognize that we don't observe this separation of scales. And so what this means is that our resolved grid scale variables can't fully constrain the subgrid scale motion. And what this means is that if we make a deterministic scheme, we are always going to have an error in our parameterized tendencies. So we can't remove this error. So instead of trying to remove it, we should characterize it. And this is what a stochastic scheme does then. It describes this subgrid scale motion in terms of some PDF that's constrained by or conditioned on the resolved scale flow. And so we're moving away from this, this assumption that we should always make the best guess forecast of the subgrid scale cloud, for example, in this figure. And we're moving towards a situation where we represent one possible evolution of the small scales in a kind of using a stochastic approach. And these stochastic schemes have been extremely useful in ensemble forecasting on weather through seasonal timescales. So here on the left, I'm showing ECMWF's ensemble forecast of Sandy 5 days ahead of landfall. And you can see that, that it's correctly predicting this left-hand turn. If we collect many such ensemble forecasts of hurricanes together, we can show that the observed track of the hurricane does behave as if it was drawn from the predicted distribution. And so that's the property which we would call reliability, so that the ensemble forecast is correctly characterizing the uncertainty in the prediction. And we can see that a lot of this reliability is really coming down to the stochastic scheme. So on the right-hand figure, I'm showing some sensitivity tests where so firstly I'll say what I'm showing here, so that the lines with the crosses is the root mean square error between the ensemble mean and the observation, and the lines with no crosses is the spread of the ensemble. And so for a reliable ensemble, these two lines should match each other. The pale grey lines show ensemble forecasts where we just make perturbations to the starting conditions, so representing initial condition uncertainty. And the other different coloured lines represent different flavours of stochastic physics. And you can see that for all of these stochastic schemes, we increase the ensemble spread, and we actually also reduce the error in the ensemble mean. So we're getting a more accurate forecast, and we're also getting a better calibrated forecast. And we also see benefits on climate timescales. And so, I mean, theoretically, the reason why this might be has also been around for a long time. So this is a quote from kind of Hasselmann's famous paper in 1976. Slow changes of climate are explained as the integral response to continuous random excitation by short period weather disturbances. So it makes sense then that if we use a stochastic parametrization to improve the variability of the short kind of timescale, the fast timescale processes, the weather in our model, we can then improve the statistics of the model on much longer timescales, on climate timescales. And this could be through a number of different routes. We see, even if we put in a zero mean stochastic perturbation, we see drifts in the model, so changes in the mean state. We see changes in the variability, and then also, other kind of nonlinear processes like noise-activated regime transitions. And we are actually seeing these impacts in climate models. So there's a lot of work that's recently been looking at the impact of stochastic schemes in climate models. I'm not going to talk about all of these examples in great detail. One thing to take away is that they quite often, we see big improvements in moist processes. So these very sensitive kind of convection and cloud processes, which I've already highlighted, are very important in our models. So maybe one which I can talk about is this result here, which was the first time that we put a stochastic scheme into a coupled climate model. And the big result that we found was that ENSO, so the El Nino Southern Oscillation, was substantially improved in that model. So this is a power spectrum of ENSO. The black line is showing the control model power spectrum compared to the observations in grey. And you can see that the power spectrum showed far too much power in ENSO, so the amplitude of ENSO was too big, and it's also too peaked, so it was a very regular oscillation between warm waters in the tropical Pacific and cold waters in the tropical Pacific. And we put in our stochastic parametrization, and we saw a really transformed power spectrum. So the switching between the El Nino and La Nina events in the Pacific is much more irregular, much better representation of what we really see. Okay, so earlier in the talk, I motivated why we might want to emulate parameterizations using machine learning, and the reasons still stand then for why we might want to emulate stochastic parameterizations. Again, we could see cost benefits, and again, we could see improved approaches. But when it comes to listing examples here for people who've done this, there actually are essentially no examples to list. So this is a really a kind of an area where there could be a lot of really fruitful research, given what we've seen about the kind of performance of machine-learned deterministic schemes, and given these past results showing how useful stochastic approaches are. And so this then really brought us to our project. Many of the operational stochastic schemes that we use are very ad hoc. The structure of the scheme has been pre-specified. The parameters in the scheme have been pre-specified, perhaps based on some kind of expert ideas of what the uncertainty should be, or through some kind of simple tuning to match spread and error. So the question that we wanted to ask is, can we improve on this very ad hoc approach by using machine learning to really learn what the scheme should look like? And so what we've then done is a set of proof of concept experiments where we're comparing a stochastic neural network to a bespoke stochastic parametrization scheme that's really been designed for the system that we're working with. And the system that we've chosen to do these tests in is called the Lorentz 96 system. So this is a very idealized model of the atmosphere, which was proposed by Ed Lorentz. And it consists of two sets of coupled equations with two types of variables. So the x variables are large scale and low frequency variables, and each x variable is coupled to many small scale high frequency y variables. And so you can see them are all arranged in a ring as shown in this schematic. And the y variables are in turn driven by what their parent x variable is doing. And so the kind of game we play goes as follows. So firstly, we integrate both of these sets of equations with a fine time stepping scheme and a small time step. And we say that the resultant evolution is the evolution of our true atmosphere. So this is what we're aiming for. We then create a forecast problem. So now what we're going to assume is that we don't have the computational resources to resolve our y variables. So just like in the real atmosphere. And so what we need to build is a forecast model for x, but where we parameterize the effect of y on x as a function of x. And what we're actually choosing here is that our parameterization of x is going to be local. So it's only going to be a function of xk, the kind of parent x variable. And this is to mimic what we do in the real atmosphere, where we have our parameterization schemes are kind of embedded within each subgrid column. And on the right-hand figure here, I'm showing the true distribution of this subgrid tendency U as a function of X. And what you can see is that there's clearly quite a strong dependency of U on X, but that it doesn't collapse onto a deterministic function. So for a particular value of X, there's a range of values of U which would be consistent. And so this is immediately motivating why we might want to take a stochastic approach. And the machine learning approach that we took in this paper is using generative adversarial networks, or GANs. And so what a GAN is it's actually a pair of neural networks. And one is called a discriminator, and one is called the generator. And so the following slides I've very gladly taken from my co-author David John Gagny. And so the characters that you see on these slides will be very familiar if you live with small people or if you're young at heart. So firstly, let's talk about our generator. And so our generator creates synthetic samples based on the training data. And so in this picture, we have some characters from the Pixar film Ratatouille. So here we've got Remy the rat, and Remy is a really good chef. And he's friends with this guy here, Linguini, who's a very bad chef. But Remy can control Linguini to do cooking and thereby create very nice dishes. So in the same way, in a GAN, we have an input to the neural network, which is our latent vector. This latent vector contains both random inputs, and that enables us to sample from the distribution, which is represented by the neural network. But in our case, we're also using the kind of conditional version of the GAN. So you can also provide information about the state of the system in that latent vector, which means that the GAN is able to represent these kind of conditional distributions. And so click forward. And so then what happens is that our generator creates a synthetic sample, which is based, kind of conditioned on this latent input vector, which contains both this random and predictive component. And so we can immediately see why this setup is going to be a good approach for stochastic parametrization. Because the stochastic parametrization problem can be framed as sampling from a kind of one tendency from some distribution of reasonable subgrid tendencies, conditioned on the resolve scale. So that's exactly what the GAN is doing. It's creating a synthetic sample that is consistent with the input latent vector. This synthetic sample is then fed into the critic or the discriminator. And so what the critic's job is to determine which of the samples it receives are real and which are synthetic. And so this critic, this discriminator, is going to get fed either a synthetic sample or a true sample, and it has to make a decision about whether it's real or not. And it feeds the features which it used to make its prediction. It then feeds back to the original generator through a kind of back propagation standard method. But in this way, the critic is acting as an adaptive loss function. So it's learning which features are able to help it identify true from synthetic samples. And the end result of this kind of sequential optimization is some equilibrium state where the critic is no longer able to discriminate real samples from fake samples. So it will just have a kind of 50% chance of being correct. And I suppose one thing to say is that while this is an equilibrium state, there's no guarantee that this is going to be a good equilibrium state or not, which will come out later in our talk. Okay, so we then wanted to design a GAN which would be good for the problem of this kind of stochastic parametrization for the Lorentz system. But the development and use of stochastic parametrizations in atmospheric models has already taught us a lot. So we wanted to use this information in developing our GAN. So the main thing that we've learned is that spatiotemporal correlations are really important for stochastic parametrization. So firstly, this is because our subgrid terms actually do exhibit spatiotemporal correlations. So on the left, I have a map I've taken from a different paper that I've worked on, looking at essentially characterizing the error in our predicted tendencies by comparing a forecast model to a high-res simulation. And you can see that while there's quite a lot of noise, there are also, larger scale features that are appearing in this map. So there are spatial correlations here. On the right, I'm showing you the real evolution of U as a function of X for the Lorentz system. And hopefully you can see that this has got a lot of temporal correlation in it. So we're not seeing a kind of white noise process here. And actually there's quite a lot of structure. We tend to cycle around this space in a somewhat anti-clockwise orientation. So there's a lot of structure in these tendencies U. From a more pragmatic point of view, if we just put white noise into our forecast models, it ends up being rapidly dissipated. So we do have to put in a spatiotemporally correlated noise to have an impact when it comes to making our weather and climate forecasts. So that then brings me to the architecture that we've chosen for our GAN. So the generator and the discriminator are two separate networks, but they both have almost identical architectures. So both of them take as an input the state of X at the previous time, the tendency at the previous time, and then our random noise perturbation. We have two dense layers, both with 16 neurons. We did try using more neurons in each of these hidden layers, but we didn't see an improved performance. So this seemed to be sufficient for this problem. We also have these kind of additive Gaussian noise layers. As you'll see later, we found that this led to quite some impact on how robust we were at finding the optimal solutions. In the generator, we have an optional final additive noise layer before the output. What are we using? We're using this CELU scaled exponential linear unit activation function, which is a kind of generalization of the more commonly used ReLU activation function. But it has some nice properties. It maintains a kind of scaling of the throughput of the network, and it also avoids the vanishing gradient problem. What else? We've got some regularization. We're using a ridge penalty. So this ensures that the GAN doesn't overfit. There was some sensitivity to this, which I'll mention later. And then here's a few details about the kind of training that we did. And for all of our models, we took whatever the state of our network was at the end of the 30th epoch. So we didn't choose the most optimal model from within. So just so that everyone had, all of the models that we test had the same amount of training data. And we tried really a very large number of configurations. So we've come up with this kind of naming convention to try and summarize what we've chosen for each. So the first option was that while many of our models took both X and the previous tendency as an input, we also tested the sensitivity to just including the state as an input. So that's the first part of the name. The second thing is that we manually set the standard deviation of the noise in the model. So that's both in the input and these additive layers in the middle. And we set it to this kind of range of values, the standard deviation. These large, medium, small, and tiny. That's the next part of the name. We tested both white and red noise. This is based on our experience of stochastic parametrizations in forecast models. We know that red noise is very important, so we wanted to test the sensitivity of this. And we estimated what the autocorrelation of our noise should be, the lag one correlation from some offline estimates of the residual of our between our GAN U and the kind of true tendency. And then finally, I mentioned in the generator that the final additive noise layer was optional. So most of our GANs include this layer, but we tested the sensitivity of this as well. So the little star means that we've turned it off. And all of these GANs we're going to compare to what we call a bespoke benchmark stochastic parametrization. So this is a stochastic scheme that has been used quite extensively for the Lorentz 96 model. It was originally laid out in Wilkes's paper back in 2005. And it's very simple. You represent the subgrid tendency as a deterministic component, which is coming from a fit to this scatter plot of the true tendency against X, and then a stochastic residual, where you measure where this residual is a red noise AR1 process, and you measure the correlation and the standard deviation from the kind of the departure of the true U's from this deterministic estimate. And this performs very well. So this is actually quite a stringent benchmark to test the GANs against. So the first thing that we did is we considered an offline verification. And this is a very common first test of any machine learned parametrization. So essentially what we did is that we, for each GAN, we tested its performance when we presented it with input X state and U tendencies from the truth run. So it was always receiving inputs that were from the true data set, and then we could see what it predicted as the tendency, and we could compare this predicted tendency distribution with the true distribution. And because there's no feedback, because this predicted U doesn't ever feed back onto the state that's fed into the next GAN, there's no difference between white and red noise in this case. So we there's no need to test that. And we're going to summarize the difference between these distributions using this Hellinger distance, which integrates over this function of the difference between the two PDFs. Okay, so I appreciate this is a very busy figure, so I'll try and talk through it. So what I'm showing here is all the different GANs that we tested. And the dashed horizontal line here is showing what the polynomial, the stochastic polynomial benchmark parametrization, how well that performs. The smaller the Hellinger distance, the better. And so what we can see is that we've tried to, the colors are helping you to group similar GANs. So for example, all of these dark gray ones have the same XU inputs and starred outputs, so no final noise layer, but they just have different values of different standard deviations of the noise. And similarly, the pale gray are the same except without the U input, so they go together with the dark gray. And then the reddish colors are similar, kind of a similar set of pairs of experiments, but now where we are using the final additive perturbation layer. So the first thing to take away is that the standard deviation of the noise does seem to impact how the GANs train. So for example, when we use a very large standard deviation, so like these red circles here, we find that it somehow limits how well the GAN is able to find the real structure of the distribution of the data. So there's just too much noise. So it starts off improving, but then it's not really learning anything at the end. If it's very small, so for example, this line with the little crosses, then we see a huge amount of variability in the distance between epochs. And so it seems that, I mean, there might be some level of overfitting, or it might be that the generator or the discriminator, one of them is getting too good, and then it's not really able, the balance is lost between the two. And so the kind of equilibrium which you're aiming for gets broken. So I suppose we're starting to see here a bit one of these issues with the GAN, which is that it can reach an equilibrium state, but there's no real, you don't know if that's going to be a stable equilibrium or if it's going to be an optimal equilibrium. And the other thing I want to point out is that whatever they land on at the end of epoch 30 is what we take as our model. And you can see that at this point, the one that's clearly the winner is this upturned triangle, so XU medium, the XU medium model. And the two that are performing very poorly are these pale grey ones here, actually. So this is the X small star and X tiny star. And the others are all kind of in the middle. The other point to note is that in general, the XU models are a bit better than their X counterparts. So for example, if we compare the red with the orange, in general, the red are lying below the orange. And similarly, the dark grey are lying below the pale grey. Okay, so we're now going to move to online testing. So we're going to test each of our GANs in how they perform in kind of free running simulations. We'll start off with looking at climate diagnostics, so running these 20,000 model time unit integrations. This is a few hundred years if you convert to a kind of atmospheric time variable. Discard the beginning as a spin-up. And so what I'm showing here is the PDF of the predicted X variable compared to the truth, which is this, this dash line here, for a subset of the models we tested. And so you can't really see the difference between many of the models. You can see that two of the models are terrible, but many of the models are doing very well. So the main thing to take away from this is that actually we are doing a really very good job at capturing a lot of the details in this PDF with our GANs. To summarize this statistic, again, we can use the Hellinger distance. So that's what I'm plotting here for all of our forecast models. Again, lower is better. So we can see a few things from this plot. So in terms of climate, it's quite interesting that the white noise schemes, which are the blue sets here, and the red noise schemes, which are the ones that are kind of reddish coloured, are really performing fairly similarly, actually. So for the same architecture, if you just change the noise colour, you do fairly similarly in terms of climate performance. What else can we see? So that another thing to note is that if we recall that offline, the best performing model was XU medium. So that's the one that I've circled here in red. And the worst performing models were X small star and X tiny star. And I've circled those in grey. And so what we can see is that it's completely different when we move to online testing. So actually these two models which did perform very poorly are among our best models now on these climate timescales. So the other thing that we remember from our offline testing was that XU was better than X. And now actually generally the XU is worse than X. So the XU are the 4 joined together, and they're generally worse than the comparative X only simulations, which are these 3 joined together, and similarly for red compared to orange. So we're seeing completely different performance online to offline. And then the final thing to note is that our benchmark stochastic parametrization is this horizontal dashed line. And really excitingly, many of our GANs are actually able to outperform this benchmark. So that's a really encouraging result. We dug into this a little bit further. So instead of just looking at the PDF, here we're looking at spatiotemporal correlations. Here the true correlations are shown in black. The polynomial is given by this line with the stars, and you can see that many of our GANs are clustering around that polynomial line, but actually our pale grey XW star model seems to be doing a bit better actually than this benchmark in terms of timing, especially of this second peak. So in general, we kind of see consistency across the board with all the different climate diagnostics that we looked at in terms of which ones perform the best. So then the final thing that we looked at is how well our models did in a weather forecasting setup. So here I'm showing a figure very similar to that one I showed in the introduction, where we're looking at the root mean square spread of our ensemble forecasts and the root mean square error between the ensemble mean and the observation, where the what do we have? The lines, the solid lines are the error, and the dashed lines are the spread. So the solid is the error and the dashed is the spread. And then the same color is used for the same model. So a reminder, what we're looking for is for these, the spread and the error to lie on top of each other, and for both the lines to be as low as possible, because that's indicating a small error in the forecast. And the polynomial model, which we're aiming to beat, does extremely well. So that's this kind of mid-gray dashed lines here. But what we can see actually is that our pale grey X small w star is actually doing as well and potentially even better than this polynomial scheme in terms of matching the evolution of the error with the spread. We can summarize this statistic again. So here I'm just going to pick the spread and error at 1 lead time and plot them on this figure. So the spread is shown in the circles and the error as the crosses for each model. So you see the polynomial model is very well calibrated. But these 2 models which did well in climate are also doing very well here in terms of reliability of the ensemble forecasts, and have a slightly even lower error than the polynomial. And the thing to note here is that, I mean, before when we went between white and red noise for climate diagnostics, we didn't see a very big impact. But here it's certainly the case that our white noise schemes, these different blue runs, are generally under-dispersive. So you can see here, for example, that the spread of the ensemble forecast for this white noise model is a lot smaller than its error, so it's too confident. And when we take the same architecture but move to the red noise approach, we see a much better spread, so seeing a big improvement in the reliability. So it seems that you can adjust the temporal correlation of your noise to improve this property of these probabilistic weather forecasts, and it doesn't have such an impact on the climate timescale in the Lorentz system. And so we summarize some of the trends we saw across models using these scatter plots. So in general, what we see is that if we reduce the root mean square error in our weather forecasts, we tend to reduce the Hellinger distance. We get a better climate. So that's very nice, seeing this consistency in performance on these different time scales. We don't see any relationship, though, between the reliability and the Hellinger distance. So it seems like reliability would be something that you could essentially tune separately from the error in your model for this case. But then the most concerning figure is this plot showing the correlation between the offline skill and the online skill. And we're not seeing any correlation here at all. And this is concerning because many machine learning parameterizations are first tested in an offline approach before you move to online. But it seems that this testing offline can tell you essentially nothing about how well the scheme might perform online for at least this kind of model that we've tested. So before I wrap up, I mean, there was quite a few surprising sensitivities, kind of health warnings that we took out of the project. So firstly, there's this rather intriguing result that using only X as an input gave much better model results than using X and U. And the reason we put in U as an additional input was that we thought it was a really neat way of building temporal correlation into the model, because we saw that for the Lorentz system, you had these very this kind of sweeping through the joint PDF of U and X. And so why not give it this extra information of the previous tendency to help it learn the next tendency? But what we think is going on here is that actually in the real Lorentz system, U is an extremely strong predictor of what U at the next time step should be. So the GAN essentially uses to, it learns to very strongly rely on U to give U at the previous time step to give U at the next time step, and it puts very little noise into the model there. Whereas actually this means that when you run it in an online mode, you end up with kind of accruing errors because it keeps very tightly to whatever it predicted at the previous time step. If you only use X, then there's a lot more uncertainty inherent in the prediction. You don't accrue bias in the same way. I mean, another thing we tried to do is actually learn the noise standard deviation. So, I mean, what I've presented here is using these just 4 different set values, but we did try and learn the noise, and that didn't work at all well. So we couldn't really achieve any degree of consistency in the convergence when we repeated the experiment. So this is why we moved away from that. There were also quite a lot of sensitivities to some of the choices that we made in the training, I suppose, in some of the hyperparameters. So the batch normalization was found to be very important for getting stable results. And there was a very strong sensitivity to the regularization that we were using in terms of this ridge penalty. And if we set the penalty too high, we ended up with very underdispersive distributions. So this is penalizing overly complicated models. But if we had it too low, we had very overdispersive distributions. So it was trying to find a sweet spot in this parameter. So to summarize then, we've built this explicitly stochastic GAN as a machine learning approach for stochastic parametrization of subgrid processes. We found that a subset of these GANs that we trained were competitive or even potentially better than a pre-designed kind of bespoke parametrization approach. We found this intriguing result with where using past tendencies is not necessarily a good idea for this situation because it led to accumulation of errors. And we also found that the correlation of the noise had a very small impact on the climate runs, but was really important for the spread of the weather ensembles. This lesson that we've learned from stochastic parametrizations about the importance of spatiotemporally correlated noise does carry through to then stochastic machine learning approaches. However, GANs are quite tricky to work with, actually very sensitive to architecture and hyperparameters. They can reach equilibrium in lots of non-optimal states, and the offline scores don't necessarily correlate with model performance. So finally then, what next? Obviously the Lorentz 96 system is a very simple testbed for machine learning approaches. And so one thing that I'm interested in exploring is whether we can use, similarly to some of the deterministic machine learning parameterizations, whether we can use coarse-grained 3D high-res model output instead. And so, I mean, we've already done work where we've used this kind of approach for constraining more traditional stochastic parameterizations. This could be a really nice approach to carry forward into a machine learning stochastic parameterization as well. So finally then, you can check out all of the code. It's published on GitHub. So David John published it here. So please do check that out. And then finally, I'll put up the reference of the paper. So thank you very much for listening.
Thank you, Hannah. It's very nice. Are there any questions? If so, just unmute and ask or raise your hand. In the meantime, I have maybe one question. We did something similar also with Lorentz 96. And we also saw that if you condition on X and what you call U, the thing doesn't work as well. You gave some explanation, but is that the same as saying that the machine learning model is overfitted to such a degree? Because it's such a strong signal if you have to predict u given u of the previous time step.
Yes, I suppose potentially. I suppose the thing, what I was thinking is that because the u at t-1 and u at t are so strongly correlated,
yeah,
that it's quite easy if what the machine learning parameterization learns is that actually, you know, taking u at the previous time step and then adding a very tiny perturbation is going to give me a good estimate, which is true for the offline testing, then I mean that's not necessarily overfitting. But then I suppose the problem is if there's a systematic error in how it, you know, in how it does this correction, you could quite quickly drift away and never have enough noise in the system to kind of pull you away from this.
Yeah.
I mean, I suppose that there's clearly some misfitting that's going on in order for these biases to accumulate in that way.
And if you would use some sort of recurrent neural network, which has this history dependent in the architecture, maybe that would work better.
Yeah, I mean, I think this GAN approach is just one of many approaches that could be used for stochastic parametrization. I mean, coming back to your question about overfitting, so we saw these accruing biases. Let me find here. So even I mean, even for some models with pretty large, large additive noise layers in the middle, which you'd think would prevent the overfitting in the training, in the training phase. So,
Hi, I have a question.
Richard, yes.
So do I understand correctly that your GANs are trained offline? And the polynomial model, was that calibrated online or offline?
No, that was calibrated offline as well. So hang on, if I come back to, I don't know if I have the best equation for this. So what we can do is estimate what this term should be from our long truth simulation. And so we essentially do this. So we've actually coarsened, in our forecast model, we've coarsened the time step. So what you can do is you can take exit a forecast time step +1 minus exit the current time step, estimate what these terms are, and then take them off here, and the residual is what the true tendency should have been. So you can then create a time series of this true tendency conditioned on the value of x from your long training data set, and use that to derive the statistics.
Yeah, I see. I wonder if there is an advantage to training the GANs in some kind of online setting, where you're actually targeting the level of prediction in the online setting rather than just the this kind of closure term.
Yeah, I think that might be beneficial. I'm trying to think. I know that some of the papers, so especially going all the way back to this slide. So I think the Brenowitz and Bretherton papers, when they were doing their machine learning for deterministic parameterizations, they had to come up with some quite interesting kind of cost or loss functions, whereby they require a good performance over many time steps, which I suppose is then trying to get at, some kind of stability and reducing accruing errors over many time steps. So I suppose that's a little bit similar, and they found good performance from that approach, and maybe we should try that as well.
Okay, thanks.
Stefan Raspe was also promoted online learning.
Yeah, it's very big in the turbulence modeling community now. Anything that's not online is called online learning is called CFD consistent, and offline is called presumably CFD inconsistent by default.
Excellent.
So
Right.
yeah, there is yeah.
It'll be interesting to think how easy it's going to be to train GANs in an online setting.
It's going to be a nightmare. I mean, cost. Yeah, in atmospheric models, it will be a nightmare.
Yeah.
Yes, I've heard.
Go ahead, Hannah. Sorry.
Oh no, I was just going to say I've heard Stefan talk about this, but I thought he'd mainly highlighted how good it would be, but how difficult it would be to then do the kind of back propagation through many time steps, I suppose. So, but it sounds like there's experience with this in other fields. Sorry, Dan, what did you want to say?
So I have a bit of a different question. So the GAN, the way you use it here, so the typical for Lorentz 96, it's predicting a scalar quantity, right? So the neural net predicts or samples from distribution for this the term that you call U, right? It's a scalar, at least because it's done independently for individual grid points.
Yes.
So I wonder, what are your thoughts on how that would scale if you go to higher dimensional quantities, where you would need to train a GAN to sample from higher dimensional distributions, right? So I'm particularly thinking of, for instance, if you try to sample quantities that, for instance, have vertical extents, right? So if you again go to the application of convection parametrization, right? So there's the essentially you're trying to predict vertical profiles rather than scalar quantities. So how would that scale up? Do you have any thoughts on?
So I don't know the answer, but I believe that GANs have been used for generating like simulated images and things like that. So I think they would, and there is work going on using GANs for kind of downscaling applications and things like this, where your output that you're predicting is more than just a single number. And so I think that there is work going on which shows potential there. I suppose for the parametrization, I mean, I don't know, it's hard to know how well it would work without testing it, I suppose, for all these things. But I think there's some indication that it could work.
Okay, that's good to know.
Maybe I can add something to that. So at least with the image generation story of GANs, one problem you run into is, I forget what it's called, but it's kind of over concentration. You tend to generate the same images or very small variants of the same images over and over again. So especially in high dimensional outputs, it's actually difficult to get probably a good Hellinger distance that you see. You'd get something that looks like samples, but you wouldn't necessarily get a good sample of the underlying PDF.
Would it be under dispersive, Richard?
I suppose it would be under dispersive. Yeah, it would be a bunch of a PDF, which is essentially a bunch of spikes in the parameter space.
Yes, I don't know. Is there any? I mean, since that has been identified as a problem, is there any more kind of machine learning folks who've tried to work out a solution to that? I think
I read like 2 papers on it once, and I tried some code, so I can't say for sure.
Yeah.
Already in the who's the guy who invented them? Is this Churchfield guy or?
Yeah. So where's my GAN slide? Here we go. So Goodfellow seems to be.
So he has a fairly recent archive paper where it's like a tutorial, and he discusses some of the limitations, and this is one of the big ones.
Okay.
And then if you try out some standard Python GAN codes of image generation, that's, you can do it pretty easily. You really run into this problem a lot, so that you get very easily GANs which, for example, when you're generating handwritten digits, produce like lots of 9s, but no 1s, for example. So your generator is basically trying to win the game by just being very narrow, by narrowly specifying, okay, I want some image, and the discriminator then can't say, all images look the same, so the discriminator can't make a difference.
Yeah. Okay. So the only other type of GAN that I've heard of is the Wasserstein GAN, which is where so in the loss function you use the Wasserstein distance, which apparently has substantial improvements, but I can't remember more details than that. But I'm not sure if that was an approach that's trying to address that problem.
I don't know.
No.
But I think in your case you have a relatively low dimensional output, and so then it's actually not such an issue for you.
Yes, it might be that a GAN is a useful, that it's difficult to use for predicting the entire tendency, but if there's something else that you'd like to predict, so some, you know, an entrainment parameter in convection or a triggering parameter or some much lower dimensional kind of input into a deterministic parametrization scheme, that you might be able to do better using this approach.
I think, Nikolai, did you want to say something? Or?
Yeah, just regarding what Richard said, I think you're referring to mode collapse, right? Yeah, I can see from your face that, yeah. But I think already Hannah, by just mentioning Wasserstein-GAN, because as far as I've seen, that's much less of a problem with Wasserstein-GAN compared to the vanilla GAN, or what we call it, which use the KL divergence. So it's mostly a problem with the first version. That being said, in higher dimensions, it's still there's a lot of other problems, but mode collapse is in general not a big problem in Wasserstein-GANs, as far as I understand. Sorry for just jumping in.
No, thank you. Yeah, I'm afraid I don't know any more about Wasserstein-GANs, but I should probably read up on it.
Any final question, perhaps? If not,
okay.
Go ahead. Yeah. No,
I was
go
just
ahead.
wondering, are you working now on trying this out on a more complex model than Lorentz 96?
So I would like to, but I think I need to find some funding or a PhD student who would like to pick up this problem. So no immediate plans, but hopefully.
Okay.
All right. Thank you, Hannah. A very nice talk.
Oh, thank you very much.
Yes.
Yeah, thanks.